All right, we're on the home stretch here with homework, so that's good. We have 11 homeworks, and this is number 7, so well, you should all be happy. We're over halfway, well over halfway, um, about just over halfway in the class, but homework we're farther along because we have project, exam, and a couple other things coming up. So homework 7, the example homework 7 rather, just to be clear, I just want to make sure on the first two that the answers are provided. I'm not going to actually show the answers because I think it's pretty self-explanatory. There's not much more that I would actually draw. I'll talk through each of them. So in part 1 or problem 1, it was to highlight or label the active chords if the lateral load is up or down on the page. So in this case, the lateral load is parallel to the walls D or B in part A. So the arrows point up and down the page. That means that the beam is smiling just as we're looking at it, or frowning just as we're looking at it. That's the beam that represents the diaphragm, of course. So we know that the chords are at the extreme elements in the top and the bottom. So you see that the very top line of beams has been highlighted and the bottom line of beams has been highlighted. Though the chord might not be right at the beams, it's going to be the perimeter element. It could be the beams. It could also be some kind of angle or plate that we put on top of the deck, depending on what kind of deck we have. It could be steel bars inside the concrete deck if we have a concrete deck. Those are capable of being the chord elements too. Moving on to problem B, or part B, exactly the same. Just remember that it's chord elements of forces in the same direction, and so no matter what we do with the reactions, the chord elements are still going to be at the same location. Uh, Same story for part C and part D. In part D, there's a little bit of an anomaly in that there's a reaction on every single column. So the diaphragms would be simply supported between each of those bays. So there's 3 bays in the direction we're talking about: the left bay, the middle bay, and the right bay. The left bay is bounded by the grid line with column A, the vertical grid line with column A, and the vertical grid line with column D. That makes up the left bay. So we're looking at that vertical column, so at the top and bottom of that, and then the same for the middle, and then the same for the third. Other than that, this problem hopefully was pretty self-explanatory for you. Going to problem 2, we're talking about drag struts. So the point here is that the drag struts are really dependent on the location of the braces, and the chord elements are not dependent on the location of the braces. So given these floor plans and the load now has switched to be left or right, what we should remember from class is that the drag struts the drag strut elements are parallel to the load, so the load is left and right, so our element should run left or right or be horizontal in this plan view. So part A, we have 4 shear walls in the center. If we want to put drag struts, there are, to note, I'm not posing a drag strut solution per se, but asking you to label all the possible drag strut elements. So in part A, the drag strut elements are highlighted yellow, and they are the beams or girders that are in line with the shear walls A and C. So if they're in line with the shear walls A and C so that they can pass load to A and C, then they can be drag strut elements. Moving down to part B, here we have, again, 4 braces, but they are on the perimeter. So the braces A and C are the ones that are active for load that's left and right. So our drag strut elements are any beams or girders in line with the braces A and the frame C. I called it a brace before, it's really a frame. Part C, this one is a tricky one. I labeled it specifically as a C shape. You know from class that when we don't have 4 elements, basically to give us 2 reactions in each direction, we have to utilize the alternate, the 90-degree elements to prevent the rotation of the diaphragm. So obviously brace A takes all of the lateral load left and right, And then the next obvious thing, or hopefully it's apparent, is that the drag struts for that direction, brace A, need to be in line with brace A. So those two top um, beams in this plan view. And then because we do engage the other braces B and C because of the rotation and not having two braces in the X direction, we also can have drag strut elements on the left and right perimeters. So you see those two yellow highlighted beams on each side that are in line with B and C. Those are also potential drag strut elements. Again, we don't have to use them, but we might need to if we don't want to increase the thickness of the deck or do other provisions to improve that. And then finally, in the cantilever column system, every single column is a lateral element, so every single beam can be a beam orchid or whatever we're calling these. Um, each of those can be a drag strip because they each connect to the lateral element. So anything that's horizontal for this direction would be okay to highlight. So we count most everything there. All right, then that takes care of the first two problems. So let's move on to problem 3. This one I'll actually work. So given the floor plan below, determine the chord forces for the following loads and dimension. So we have some kind of floor plan that looks like a pretty basic big rectangle. We have 75 feet in the vertical direction, 75 feet, and 150 feet in the horizontal direction. It's not important for me to label or to show the columns in the framing, so I'm not going to. I do have this load 500 pounds per foot. And then let's go ahead and take a look. So the important thing to figure out is the reaction. So we have a reaction in this direction at brace B and brace D as in dog. And A and C are not active in this case because we have two reactions in the Y direction. We don't need to utilize the reaction in the X direction. So if I were to draw our beam that represents that diaphragm, it looks something like this. And we have this 500 pounds. Again, you can point the arrows up if you want. Laterally, the direction arrows are a lot less important because remember we always design for wind going both ways and seismic going both ways, so we end up using the absolute value. So I'm going to go ahead and point them down, and hopefully that's not confusing, but if it is, just let me know. And so then let's use find out the moment. Remember from class there's several ways to do this. We can cut the beam at the center, eliminate the right side, take a look, determine what the moment is by the cuts. We can draw the bending moment diagram, or we can use an equation that we derived last semester and some of you may start to remember. On your exam, I think I put this on one of the equation sheets, so you'll have it. WL squared over 8, this is for a simply supported, so that means we have a pin on the left and a pin or a roller on the right, and a uniform load, W. So if I plug in our variables, 500 pounds per foot, the length L is 150 feet. Of course, it is squared divided by 8. Go ahead and do that math with the calculator. 1406 kip feet. I went ahead and moved the decimal place to go in kips because it's easier to work with 1400 instead of 1,400,000. So I am going to go ahead and say my final answer is that for the moment. Now the question is really asking for the chord forces, so don't forget from class, F equals m over d because moment equals force times distance. The distance between our two chord elements is 75, and again the moment is 1406 kip feet divided by 75 feet equals 18.8 kips. So the chord force in that rectangle, 18.8 kips. Now, part 2, let's determine if we require determine the required diaphragm shear. Sorry, So we're not utilizing drag struts because I said not to utilize drag struts. And so we need to find out what is the diaphragm shear um, minimum capacity. We're looking for a capacity. So this is problem 4. And we know we have the braces that are active are what we showed above. I'm going to circle them in green for you. These are the 2 braces. We know that their length is 1/3 of the length, and so since the total is 75, we know that this is 25. We know that the reaction at each end is equal to half of the total. So we have 500 pounds per foot times that 150 feet divided by 2, because it's half of the total. And let's see, that comes out to be 37.5 kips. Check me on that, but hopefully that's what you got also. So that's the reaction to each brace. So there are, into this brace, 37.5 kips, and into this brace, 37.5 kips. Okay. Now we got to determine the diaphragm shear. So hopefully remember from class that's going to be just the uniform load. So we'll say V, I'll call it little v. This is going to be the diaphragm shear. We have F divided by distance, or the length. Might be more appropriate to use length, I'm sorry. So that's the F 37.5 kips divided by the length of 25 feet. That's the length of the brace. This comes out to be 1,500 pounds per foot. So what that tells us is for the diaphragm, that deck, to be able to pass the load to this brace over this 25-foot distance, it has to have at least an attachment capacity of this 1,500. If it does not, if it has something less than that, the diaphragm will simply break away from the brace and not transfer any of the load. And once we detach the brace like that, suddenly we don't have a structure that stands up. So it's not a good situation. We don't want to ever have it. So that concludes the homework 7. 8 is coming up, so hopefully this was helpful. If not, let me know.